Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we will start our study of bivariate probability distributions. That is, now we're going to study two random variables at the same time. So, in this video, what we're going to be doing is discussing an example where we present a bivariate probability distribution, and hopefully that example will show you how the concepts that we have already discussed for one single random variable, how those concepts and ideas can be easily extended to the bivariate case. Okay, so first, let me show you the definition of bivariate probability distribution in the case of discrete random variables. So we have two of them now, and the joint probability function, right, is going to be just defined like this: the probability that the random variable y1 equals a particular value, and that the second random variable y2 is equal to another value. Okay, and we want these functions to be defined between negative infinity and infinity, right? Both of them. Okay, so now let me show you a theorem that we have here that you will see. We're not going to give the proof of this theorem, but I want you to see that the ideas are just extensions of what we saw in the case of one single random variable. So if you have a joint probability function, right, before, when we had a discrete random variable, we had something called the probability mass function. Okay, so now this function describes both random variables y1 and y2. Okay, but now those numbers assigned by that probability function are also numbers that satisfy those two conditions that we discussed before. Each of those numbers must be between 0 and 1, and when you add them all up, you should end up with a 1. Okay, so those are the two characteristics, the two conditions that a joint probability function must satisfy in order to be a legit joint probability function. So just like before, but now instead of evaluating that function at just one point, just 1 point, we have 1 point in the real line. Now we have a point in the plane, right? We have two coordinates here, but the ideas, as you can see, are the same. Okay, so now let me illustrate this using an example. That's the problem that we would like to solve together in this video. Okay, so take a look at it, and what we're going to be doing is obtaining that joint probability function, okay, for these two random variables of interest, y1 and y2. Okay, got it? Did you take a look at that slide? Did you read it? Okay, so we're going to proceed in a similar fashion as we would for the univariate case, back when we had only one single random variable. Okay, so the first step would be defining the random experiment. Okay, so as you can see, in this case what we have is 3 checkout counters, right? And we have two customers these guys arrive at different times. We're assuming that they make their decisions independently and at random, okay? And the random variables of interest here are, the number of customers who chose counter 1, and y2 is similar, but that would be a variable that keeps track of the number of customers that selected counter 2. Okay, so let's try and find the joint probability function for y1 and y2. As before, as we said, first we need that random experiment. So let me very quickly describe that here. Random experiment. Two customers selecting a counter at random, and they do that independently. Okay. Next step, we have our random experiment. Let's find the sample space. So here we have to make a decision as to how we're going to be representing the sample space. So what I'm going to be doing here is I'm going to be using two coordinates. Okay, so the first coordinate represents the selection made by customer 1, and the second coordinate represents something similar, but it's the selection made by customer 2. Okay, so I'm going to be using points in the plane to denote the outcome. Okay, so we know that we could use the Greek letter uppercase O, omega, right, to denote the sample space. Okay, so here we go. For instance, 1, 1, given that I'm using that notation for the selection made by customer 1, selection made by customer 2, that means that the first customer, right, selected counter number 1, and that the second customer selected, also counter number 1. On the other hand, 1, 2 means that the first customer went to counter number 1, second customer went to counter number 2, and so on. So now you can clearly see that our sample space contains the following 9 points, right? Those are all the possibilities that we have. Okay? And let me just quickly go back to the slide here, to the statement of the problem. So see that we have 3 checkout counters, okay, and only 2 customers. Okay, so that's why our sample space looks like this. For instance, that point means that the first customer went to checkout number 3, checkout counter number 3, and the second one, the second customer went to checkout counter number 1. Okay, makes sense? Now, we are also told that these guys made that decision randomly. Okay, so, and independently. So for instance, this guy has a probability of the probability of selecting, for instance, counter number 1 is 1/3. You have 3 possibilities, 3 counters, and then when you since these are independent, we know that if we have independent events, the probability of A and B is just the probability of the product. So the product would be here, in this case, 1 over 9, meaning the probability of each of these points is 1 over 9. Okay? So just keep that in mind. Okay, now, random variables. We have 2. Now we have y1, and as we said, y1 represents the number of customers who choose counter 1. y2, something similar, but for counter number 2. Number of customers who choose counter number 2. Okay. Got it? And that's what they said, right? y1, number of customers who choose counter 1. y2, number of customers who select counter 2. Okay? Okay. So, let's keep going. Remember when we said before, when we were talking about just one single random variable, we said the probability distribution is nothing but a list of possible outcomes with the corresponding probabilities, right? The list of all possible outcomes, okay? So in this case, so y1 could assume which values? 0, right? Out of those 2 customers, none go to counter 1. 0 or 1 or 2, right? Same goes for y2. But the thing is that now we will study these 2 random variables at the same time, okay? So now what we need is something like this. Probability that y1 equals 0, for instance, that y2 equals 0, right? That would be 1. Another possibility, probability that y1 equals 0, but y2 equals 1. y1 equals 0, y2 equals 2, right? And then we are going to have something similar for y2 being 0 here. Well, y1, sorry, being 1 here. y1 being 1, right? That's another set of possibilities. And then we have another one where y1 could be 2, right? Okay, so if we can find the probabilities for those outcomes, then we're done. That's the joint probability function that we're looking for. Make sense? Okay, so now let's see. Let's try and find the probability that y1 equals 0 and y2 equals 0. That means that out of these 2 customers that we're keeping track of, none of them went to counter 1 and none of them went to counter 2. And the only way that that could happen is if we observed this, that both customers went to counter number 3. Okay, so let me just say that that's a probability of that outcome, of that point 3, 3, and we said that each of these simple outcomes has the same probability of occurring, so that's 1 over 9. You guys agree? let's try and find another one. Now we want the probability that y1 equals 0 and y2 equals 1. So that means that none of our two customers went to counter number 1, but one of them went to counter number 2, right? So if that's what happened, what we observed was this: 3, 2 or 2, 3, right? In that case, no, it would be, let me see, it would be 3, would be this guy. Yeah, that's the one. 3, 2 and 2, 3, because that means that the number of customers who went to counter number 2, we have only one, right? And none to counter number 1. Okay, makes sense? Again, so y2 is the number of customers who chose counter number 2, and since y2 is 1 and y1 is 0, the only way that that could happen is if one of the customers went to counter number 3 and the other one to counter number 2. So it's a probability of those 2 points, or, right, 2,3. So that would be 2 over 9. Make sense? Now, if y1 equals 0 and y2 equals 2, that means that both customers went to counter number 2. And the only way that that could happen is if you observed that point here, 2, 2, right? Both of them selected counter number 2. Make sense? So let's quickly finish the other ones. So y1 equals 1, y2 equals 0, right? That would be 1, 3 or 3, 1. You guys agree? Right? So that's 2 over 9. Now y1 equals 1, y2 equals 1, okay? So that would be 1, 2 or 2, 1, right? So again, 2 over 9. Now let's take a look at this one. If y2 equals 2, then y1 can't be 1. We only have 2 customers. So that probability is 0, right? Let's find the remaining ones. y1 equals 2, y2 equals 0. That means that we observed 1, 1, right? So that probability would be 1 over 9. And this one, just as before, if y1 equals 2, y2 can't be 1. We only have 2 customers. So the probability of that happening, 0. Finally, probability of y1 being equal to 2 and y2 being equal to 2 at the same time, impossible. So probability 0, right? So again, this is the joint probability function for these 2 random variables y1 and y2. Okay, let me quickly go back to our lecture notes so I can show you that in our lecture notes what we have is, you know, kind of a different version of what we just did here together, especially the way that we expressed the joint probability function. Okay, we expressed that as a so let me check why we're not seeing. Okay, I'm back. So as I was saying in our lecture notes, what I did is I expressed the joint probability function in a different way. I used a tabular format, but you can see, for instance, that first column here, 1 over 9, 2 over 9, 1 over 9 is 0, 0, 0, 1, 0, 2, right? So y1 equals 0, y2 equals 0, that's 1 over 9, 0, 1, 2 over 9, 0, 2, 1 over 9. As you can see, that's what we have here. Okay, so just a different way of expressing the same information, right? I also made a graphical representation for you to see, right? Can you see that it's similar to a probability mass function, right? But now our possible outcomes are not points in the real line, but are points in the plane, and then we assign to each of those points in the plane here in that lattice we assign a height, and the sum of the heights of those needles must be equal to 1, and the heights of those needles must be numbers between 0 and 1, just like before, right? So it's a natural extension of the ideas for probability mass function, okay, for a single random variable. Okay, so that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.